Understanding the Solar System Experiment.
Hello, my name is Caelan Hearne and my ZID is 5358977.
Kepler's first law, the law of ellipses, states that planets move in elliptical orbits with the Sun at one of the two foci. Earth's orbit is nearly circular, whereas Mercury's orbit is more elliptical, meaning its distance from the Sun varies more than Earth's. Kepler's second law, the law of equal areas, states that a line segment joining a planet and the Sun sweeps out equal areas in equal time intervals. Earth moves faster in January when it is closer to the Sun, and slower in July when it is farther away. Kepler's third law, the law of harmonies, states that the square of a planet's orbital period is proportional to the cube of its semi-major axis. Planets that are farther from the Sun take much longer to complete one orbit than those closest to the Sun. Neptune takes 165 Earth years to orbit the Sun once. Question 9. Does the planet move as the Moon orbits? Yes. Both the Moon and Earth orbit the common center of mass between them, causing the Earth to slightly wobble as the Moon orbits. Where are the centers of mass in each scenario from questions 1, 4, and 7? In question 1, it is extremely close to the center of the Sun, since the Sun's mass is vastly greater than the Earth's. In question 4, the center of mass remains nearly the same as question 1, due to the negligible mass of the planet compared to the Sun. In question 7, the center of mass moves slightly away from the center of the Sun, because the Sun's mass is now lower relative to the planet. How is the planet-Moon center of mass different to the Sun-planet scenarios in question 9b? The relative mass difference between the planet and the Moon is much smaller than that between the Sun and a planet. This means that the planet experiences a much more noticeable orbit around the center of mass. Question 11. When the grid lines are turned on, what is the distance between each marking in astronomical units? The distance is 0.5 astronomical units. This slide shows the figures of screenshots taken from the planetary orbit simulation at 1, 0.5, 1.5, and 2 astronomical units, with the velocity altered so that the orbits are circular. This slide compares the simulated orbital periods obtained from the planetary simulation with the results obtained via Kepler's third law calculations. The results obtained from the planetary simulation closely follow Kepler's third law. Any discrepancies between them would be from the manual adjustment of the velocity in the simulation not being perfect. Question 15. Which planet in our solar system has the fastest orbital velocity? Mercury has the fastest orbital velocity because it is closest to the Sun. Likewise, Neptune has the slowest orbital velocity as it is the furthest from the Sun. The reason for this is that the orbital velocity of a planet is determined by Newton's version of Kepler's third law. Essentially, planets closer to the Sun experience stronger gravitational pull, requiring higher speeds to maintain stable orbits. Planets farther away experience weaker gravitational attraction, allowing them to move more slowly while still remaining in orbit. Through this experiment, I learned how Kepler's laws govern planetary motion. I learned how the mass of a planet does not significantly affect its orbit around a star. I learned how the orbital shape changes based on initial velocity. I learned how gravity is a mutual force. Even the Sun moves slightly due to the planets. And I learned how the center of mass determines the motion of systems, and the effect is more noticeable in a planet-Moon system, where the relative mass difference is much smaller compared to a star-planet system.